Before Werner Heisenberg ever questioned certainty, science was built upon it. For centuries, the dominant belief among scientists was that the universe operated like a perfectly constructed machine. Every movement, every interaction, every change followed strict, predictable laws. If something appeared uncertain, it was assumed to be the result of human ignorance or inadequate instruments, not a flaw in nature itself. The task of science, therefore, was clear: measure more precisely, calculate more accurately, and uncertainty would eventually disappear. This world, you began with Isaac Newton in the 17th century. Newton's laws of motion and universal gravitation offered a stunningly successful framework for understanding the physical world. From the fall of an apple to the motion of planets, everything could be described using mathematical equations. Time flowed uniformly, space was absolute, and cause always preceded effect in a clean, logical chain. Once the initial conditions of a system were known, its future behavior could be predicted with certainty. This idea became known as determinism, and it shaped scientific thinking for over 200 years. By the 19th century, this deterministic vision appeared nearly complete. Pierre-Simon Laplace famously imagined a hypothetical intellect, later called Laplace's demon, that could know the position and velocity of every particle in the universe. For such an intellect, the future and the past would be equally clear. Nothing would be uncertain. This was not considered philosophical fantasy. It was a logical extension of classical physics. Nature, in this view, held no mysteries in principle, only puzzles awaiting better calculation. Electromagnetism strengthened this confidence. James Clerk Maxwell unified electricity, magnetism, and light into a single set of elegant equations. These equations described waves propagating smoothly through space, reinforcing the idea that nature was continuous and predictable. Energy flowed gradually, not in jumps. Physical quantities could, in theory, be measured with unlimited precision. The success of Maxwell's theory made many physicists believe that only minor details remained to be filled in before physics was complete. At the dawn of the 20th century, this confidence was so strong that some prominent scientists warned students against entering physics, claiming that all the major discoveries had already been made. The universe seemed mapped, charted, and tamed by mathematics. Certainty was not just an expectation, it was a scientific virtue. A theory that introduced randomness or fundamental limits to knowledge would have been viewed as deeply suspicious. Yet beneath this surface of confidence, cracks were already forming. Experiments involving heat radiation revealed inconsistencies that classical physics could not explain. The so-called ultraviolet catastrophe showed that classical theories predicted infinite energy output at high frequencies, an obvious absurdity. Similarly, experiments with atoms and light began to produce results that defied deterministic explanation. These anomalies were initially treated as technical problems, not as signs of a deeper crisis. Max Planck's solution to blackbody radiation in 1900 was the first serious rupture. To make the equations work, he proposed that energy could only be emitted in discrete packets, later called quanta. Planck himself viewed this as a mathematical trick rather than a fundamental truth. He remained committed to determinism and believed that continuity would eventually be restored. Still, a door had been opened. Albert Einstein pushed that door wider with his explanation of the photoelectric effect in 1905. Light, long understood as a wave, behaved like a stream of particles under certain conditions. This wave, particle duality, challenged classical intuition but did not yet destroy certainty. Einstein himself remained a determinist at heart. He believed that hidden variables might one day explain the apparent randomness of quantum phenomena. At the same time, Ernest Rutherford's discovery of the atomic nucleus revealed that atoms were mostly empty space, with electrons somehow orbiting a dense core. Classical physics predicted that such electrons should rapidly lose energy and collapse into the nucleus. Yet atoms were stable. Niels Bohr attempted to resolve this by imposing quantized orbits, allowing electrons to exist only at certain energy levels. While this model worked mathematically, it relied on rules that had no explanation within classical physics. Despite these growing contradictions, the scientific mindset remained focused on restoring certainty. Physicists believed that these strange behaviors were temporary obstacles on the path toward a deeper, more complete deterministic theory. The language of probability was used reluctantly, as a placeholder for missing knowledge rather than a statement about reality itself. Measurement was seen as a passive act. Observers were thought to simply reveal properties that already existed, independent of observation. An electron had a definite position and velocity whether or not anyone measured it. Any uncertainty was blamed on experimental disturbance or lack of precision. Better instruments would eventually eliminate these problems. This belief extended beyond physics into philosophy. The Enlightenment had championed reason, objectivity, and universal laws. Human progress was tied to the idea that the world was fully knowable through rational inquiry. To suggest that nature itself imposed limits on knowledge was to challenge not just science, but the intellectual foundations of modern civilization. Young physicists were trained within this framework. Mathematical rigor, precision, and predictability were the gold standards of good science. Intuition was shaped by classical imagery particles as tiny billiard balls, forces acting smoothly across space, time ticking forward uniformly for all observers. Even as anomalies accumulated, they were squeezed into this familiar mold. It was into this world that Werner Heisenberg was born in 1901. He grew up at the exact moment when certainty still reigned publicly, even as it was quietly unraveling behind laboratory doors. His education emphasized classical mechanics and mathematical discipline, but he was also exposed to the unresolved tensions at the heart of modern physics. Unlike many of his predecessors, Heisenberg would not try to preserve certainty at all costs. The demand for certainty before Heisenberg was not merely scientific. It was psychological. Certainty provided comfort. It promised control over nature and, by extension, over human destiny. Industrialization, engineering, and technological progress all depended on predictable laws. A universe governed by probability seemed unstable, even threatening. Yet the experiments did not lie. The more precisely scientists probed the microscopic world, the stranger it became. Spectral lines appeared sharp and discrete. Electrons jumped between energy levels without traversing the space in between. Classical trajectories dissolved under scrutiny. Still, most physicists clung to the hope that these were signs of an incomplete theory, not a fundamental breakdown of certainty. This tension defined the scientific atmosphere of the early 20th century. Physics stood at a crossroads, though few recognized it at the time. One path led toward preserving determinism by adding complexity, hidden mechanisms, unseen variables, deeper layers of order. The other path required a radical rethinking of what it meant to know something about nature. Heisenberg would choose the second path, but before he did, the world of physics had to reach the limits of its old assumptions. The demand for certainty had driven extraordinary success, Yet it had also become a constraint, blinding scientists to new ways of understanding reality. The stage was set for a transformation, one that would not merely adjust existing theories, but overturn the very idea that the universe must be completely knowable in precise terms. This was the world before uncertainty became a principle rather than a problem, a world confident in its equations, faithful to determinism, and unaware that certainty itself was about to be questioned at the deepest level imaginable. Werner Heisenberg did not begin his scientific journey with the intention of overthrowing certainty. In fact, he was trained within the same rigorous traditions that had defined physics for centuries. What made him different was not rebellion, but sensitivity, an unusual willingness to question whether the familiar ways of thinking were actually faithful to nature. His revolutionary approach emerged not from arrogance, but from frustration with ideas that no longer worked. As a student in the early 1920s, Heisenberg was immersed in a field in crisis. Classical mechanics, so powerful at everyday scales, failed spectacularly inside the atom. Electrons refused to behave like particles moving along neat paths. Attempts to picture atomic structure using visual models led to contradictions and mathematical inconsistencies. Instead of clarifying reality, these models obscured it. Heisenberg felt that physics had become trapped by its own imagery. Unlike many of his contemporaries, Heisenberg was not strongly attached to visualization. He was more comfortable with abstract mathematics and logical structure than with physical pictures. This became his greatest strength. He began to suspect that insisting on visual models, electrons as tiny planets, or waves rippling through space, was a mistake inherited from classical thinking. Nature at the atomic scale might not be visualizable at all. This realization marked a profound shift in his thinking. Heisenberg asked a simple but radical question: what if physics described only what we can observe, rather than what we imagine exists behind observations? Instead of trying to define where an electron really is, he focused on measurable quantities, such as the frequencies of light emitted when electrons jump between energy levels. These quantities could be observed and recorded. Anything beyond them, he argued, was metaphysical speculation. This approach required intellectual courage. Physics had long assumed that measurements revealed pre-existing properties. Heisenberg was suggesting that some properties might not exist in a definite form until measured. This idea went against common sense and centuries of scientific habit. Yet it aligned perfectly with experimental results. While suffering from severe hay fever on the remote island of Helgoland in 1925, Heisenberg experienced the breakthrough that would define his career. Isolated from distraction, he developed a new mathematical framework that described atomic behavior without relying on classical trajectories. The mathematics was strange and unfamiliar. Quantities that were once thought to commute, meaning their order did not matter, now behaved differently. Multiplying them in one order produced a different result than multiplying them in another. This non-commutative structure was shocking. In classical physics, the order of operations does not affect physical reality. In Heisenberg's new theory, it did. This subtle mathematical feature would later reveal deep truths about nature itself. At the time, Heisenberg did not fully understand its implications, but he sensed that he had touched something fundamental. The theory, later formalized with the help of Max Born and Pascual Jordan, became known as matrix mechanics. It was not intuitive. Even Heisenberg admitted that he did not fully grasp its meaning at first, but it worked. It accurately predicted spectral lines, atomic transitions, and experimental results that classical physics could not explain. For the first time, atomic behavior could be calculated consistently without visual contradiction. What made Heisenberg's approach revolutionary was not just its success, but its philosophy. By removing unobservable quantities from the theory, he stripped physics down to its operational core. Reality was no longer described in terms of hidden mechanisms, but in terms of relationships between observations. Physics became less about picturing the world and more about predicting the outcomes of interactions. This shift deeply unsettled many physicists. The desire to know what is really happening had always driven scientific curiosity. Heisenberg's framework seemed to deny access to that deeper reality, but Heisenberg did not see this as a loss. He believed that insisting on classical notions of reality was distorting our understanding, not enhancing it. His collaboration with Niels Bohr sharpened this perspective. Bohr emphasized complementarity, the idea that certain descriptions of nature are mutually exclusive yet jointly necessary. For example, light could be described as a wave or a particle, but never both at the same time. Heisenberg's mathematics provided the formal backbone for this philosophical insight. Together, they argued that nature does not conform to human expectations of clarity and completeness. Heisenberg's way of thinking redefined what it meant to explain something scientifically. Explanation was no longer about reducing phenomena to familiar images, but about identifying the limits within which concepts could be meaningfully applied. Classical concepts like position, velocity, and trajectory were not wrong. They were simply inappropriate at the quantum scale. This redefinition of explanation demanded humility. Heisenberg openly acknowledged that human language and intuition evolved for a macroscopic world and may fail when applied to the microscopic domain. Instead of forcing quantum behavior into classical molds, he allowed mathematics to guide interpretation, even when it led to uncomfortable conclusions. His approach also changed the role of the observer. Measurement was no longer a passive act of discovery. It became an interaction between observer and system. The tools used to measure atomic phenomena influenced the outcomes obtained. This did not mean reality was subjective, but that it was relational. Properties emerged from interactions, not from isolated objects existing independently. Heisenberg's intellectual style was marked by restraint. He avoided grand metaphysical claims and focused on what could be said precisely. This discipline distinguished him from both classical determinists and speculative mystics. He insisted that quantum mechanics was not a statement about human ignorance, but about the structure of physical law itself. Despite its abstract nature, Heisenberg's approach proved extraordinarily powerful. It laid the foundation for modern quantum mechanics and influenced every major development that followed. Schrödinger's wave mechanics, though more visual, was mathematically equivalent to Heisenberg's formulation. The two theories appeared different, but described the same underlying reality. What truly set Heisenberg apart was his willingness to accept that nature might resist complete description. Where earlier physicists sought certainty as the ultimate goal, Heisenberg recognized that certainty itself could be an illusion. His thinking marked a turning point in the history of science, a move away from domination toward dialogue with nature. This shift did not happen overnight, nor was it universally accepted. Many physicists struggled with the implications of abandoning classical clarity. Yet the success of Heisenberg's methods left little room for denial. Experiments repeatedly confirmed predictions derived from his abstract mathematics. In redefining how physics should be done, Heisenberg did more than solve technical problems. he transformed the scientific mindset. He showed that progress sometimes requires letting go of deeply held assumptions, even when they feel inseparable from reason itself. His revolutionary way of thinking did not replace certainty with chaos. It replaced false certainty with a deeper, more honest understanding of nature. This was only the beginning. From these ideas would emerge the uncertainty principle, a concise expression of the limits Heisenberg had already sensed. But even before that principle was formally stated, his work had already changed science forever by teaching physicists how to think when familiar concepts fail. By the time Werner Heisenberg articulated the uncertainty principle, the foundations had already been quietly laid by years of struggle, abstraction, and intellectual courage. What appeared to the world as a single, shocking statement in 1927 was in fact the natural outcome of a deeper realization that the act of measurement at the quantum scale is inseparable from reality being measured. The principle did not emerge as a philosophical declaration, but as a precise mathematical result rooted in the structure of quantum mechanics itself. At the heart of the uncertainty principle lies a simple but unsettling truth. Certain pairs of physical properties, most famously position and momentum, cannot both be known with arbitrary precision at the same time. This is not due to technological limitation or experimental clumsiness. Even in a perfect laboratory with ideal instruments, the limitation remains. The universe enforces it. To understand why this was so radical, one must recall how measurement was understood before Heisenberg. In classical physics, measurement was assumed to be passive. A ruler did not change the length of an object, and a stopwatch did not alter the passage of time. The observer could, in principle, step outside the system and record its properties without influencing them. Any disturbance caused by measurement was treated as a practical problem, not a fundamental one. At the quantum level, Heisenberg realized this separation collapses. To measure the position of an electron, one must interact with it, typically by scattering light or another particle. But light itself carries energy and momentum. The very act of observing the electron changes its state. If one uses high energy light to pinpoint the electron's position more accurately, the interaction disturbs its momentum more violently. Precision in one quantity necessarily produces uncertainty in the other. This insight was initially illustrated using thought experiments, such as Heisenberg's gamma-ray microscope. In this imagined device, short wavelength light is used to locate an electron precisely. Shorter wavelengths provide better spatial resolution, but they also carry greater momentum. When such a photon strikes the electron, it transfers an unpredictable amount of momentum, making the electron's subsequent motion uncertain. The trade-off is unavoidable, yet the true power of the uncertainty principle does not rest on such analogies. Its deepest justification lies in the mathematical structure of quantum mechanics. In Heisenberg's formulation, physical quantities are represented by operators that do not commute. This non-commutativity means that the order in which measurements are considered matters. From this mathematical fact follows a precise inequality. The product of the uncertainties in position and momentum can never be smaller than a fixed value determined by Planck's constant. This constant, incredibly small at everyday scales, sets the boundary between classical and quantum behavior. For macroscopic objects, the uncertainties are so tiny that they are effectively irrelevant. A baseball has a position and momentum that can be measured with extreme precision, making classical mechanics an excellent approximation. But for electrons, atoms, and subatomic particles, Planck's constant dominates. Uncertainty becomes unavoidable and significant. Heisenberg was careful to emphasize that uncertainty does not mean vagueness or confusion. Quantum mechanics allows for extraordinarily precise predictions, just not of individual outcomes in isolation. Instead, it predicts probabilities with astonishing accuracy. The theory does not say where a single electron will land on a screen, but it predicts the statistical pattern formed by many electrons with remarkable precision. Determinism is replaced not by chaos, but by statistical law. This shift deeply troubled many physicists, including Einstein. Einstein argued that the uncertainty principle reflected incomplete knowledge rather than a fundamental property of nature. He believed that hidden variables might exist, unknown factors that, if discovered, would restore determinism. Heisenberg and Bohr disagreed. They maintained that quantum mechanics was complete within its own domain, and that uncertainty was not a temporary inconvenience, but a permanent feature of reality. The debate was not merely technical, it was philosophical. The uncertainty principle challenged the classical idea that physical systems possess well-defined properties independent of observation. In quantum mechanics, properties such as position and momentum do not simultaneously exist in a definite form. They are contextual, emerging through interaction. Reality becomes less like a fixed stage and more like a dynamic process. This idea forced a reconsideration of what it means to know something in science. Knowledge could no longer be equated with certainty about individual events. Instead, it involved understanding the range of possible outcomes and the probabilities governing them. The role of theory shifted from providing exact predictions to defining the limits within which predictions are meaningful. Heisenberg understood that this was not a retreat from realism, but a refinement of it. Quantum mechanics does not deny the existence of an external world. It denies only the assumption that this world must conform to classical categories of description. The uncertainty principle marks the boundary where those categories lose their applicability. The consequences of this realization spread rapidly. Atomic structure, chemical bonding, and nuclear physics all required uncertainty for their stability. Without it, electrons would collapse into atomic nuclei, and matter as we know it would not exist. Uncertainty, far from being a defect, is a condition for the very structure of the physical world. Beyond physics, the principle resonated with broader intellectual currents. Philosophers saw in it a challenge to strict determinism and a confirmation of limits long suspected by epistemology. The idea that knowledge has inherent boundaries echoed themes from Kant and earlier thinkers, now grounded in experimental science rather than speculation. Heisenberg himself resisted exaggerated interpretations. He did not claim that consciousness creates reality, nor that science had abandoned objectivity. He insisted that quantum mechanics remained a precise, objective theory. What had changed was the understanding of what objectivity entails. Objectivity no longer meant detachment from the observer, but consistency across observations and experiments. The uncertainty principle also altered the scientific attitude toward explanation. Instead of asking why a particular event occurred, physicists increasingly asked how often it occurs and under what conditions. Laws became statistical rather than absolute. This required a new kind of intuition, one that could accept probability as fundamental rather than provisional. As the principle gained acceptance, it became a symbol of the quantum revolution. Yet it was often misunderstood in popular culture as a statement about human limitations or philosophical doubt. In reality, It is one of the most rigorously tested principles in all of science. Every modern experiment in quantum physics confirms it with extraordinary precision. Heisenberg's achievement was not simply the formulation of an inequality. It was the recognition that the quest for certainty had reached a natural limit. By identifying that limit, he did not weaken science, he strengthened it. He showed that honesty about what cannot be known is as important as precision about what can. This realization marked a turning point. Physics no longer sought to eliminate uncertainty, but to understand and work within it. From this acceptance would emerge technologies and theories that reshaped the modern world. The birth of the uncertainty principle was, in essence, the moment when science learned to live without absolute certainty, and discovered that it could see further because of it. When uncertainty entered the heart of physics, it did not arrive quietly. It spread outward, reshaping not only equations and experiments, but the way scientists, philosophers, and even ordinary people thought about reality itself. What Werner Heisenberg introduced was not merely a technical limitation on measurement. It was a fundamental change in how the universe could be understood. The consequences of this shift reached far beyond the laboratory, challenging assumptions that had guided human thought for centuries. In physics, the immediate impact was transformative. Classical mechanics had relied on the idea that the universe evolves smoothly and predictably from well-defined initial conditions. With uncertainty now built into the foundations of physical law, this picture collapsed at the microscopic level. Particles no longer followed precise trajectories. Instead, their behavior was described by probability distributions, wave functions, and likelihoods. Physics was forced to abandon the comfort of exact prediction for individual events. This did not mean that physics became vague or unreliable. On the contrary, quantum mechanics proved astonishingly precise in its predictions. The uncertainty lay not in the theory, but in the nature of what could be predicted. Instead of forecasting single outcomes, physics learned to predict patterns. A single radioactive atom decays unpredictably, but a large collection decays with clock-like regularity. This statistical certainty replaced classical determinism as the new form of scientific reliability. The structure of matter itself turned out to depend on uncertainty. Electrons in atoms do not spiral into the nucleus precisely because their position and momentum cannot both be sharply defined. The fuzziness imposed by uncertainty keeps electrons spread out in stable orbitals. Chemical bonding, molecular structure, and the periodic table all rely on this quantum behavior. Without uncertainty, matter would collapse, and the complex structures of the universe would not exist. Uncertainty also reshaped the concept of causality. In classical physics, every effect had a clearly identifiable cause. In quantum physics, causes still exist, but they operate within probabilistic frameworks. Events are governed by likelihoods rather than certainties. This does not imply randomness without order, but it does mean that the future is not uniquely determined by the past at the smallest scales. The universe allows multiple possible outcomes, constrained by probability rather than fixed destiny. This change forced physicists to rethink the meaning of explanation. Explaining a phenomenon no longer meant tracing a single chain of cause and effect. Instead, it meant identifying the mathematical structure that governs probabilities. The question shifted from what exactly will happen to what can happen and how likely is each possibility. This subtle shift altered the tone and ambition of scientific inquiry. The philosophical implications were profound. For centuries, Western philosophy had been deeply influenced by the success of classical physics. Determinism had shaped views on free will, responsibility, and the nature of knowledge. If the universe was fully determined, then freedom seemed illusory, and uncertainty was merely a reflection of ignorance. Heisenberg's uncertainty undermined this world view at its root. Philosophers were forced to confront the possibility that indeterminacy is woven into the fabric of reality. This did not automatically solve debates about free will, but it reopened them. The universe was no longer a rigid machine unfolding inevitably from initial conditions. It allowed room for genuine openness, at least at the fundamental level. Whether this openness extended meaningfully to human choice remained debated, but the door was no longer closed by physics itself. Epistemology, the study of knowledge, was also affected. The uncertainty principle imposed limits not just on what we can know, but on what can meaningfully be said to exist. If certain properties do not have definite values until measured, then knowledge is no longer a simple mirror of reality. It becomes relational, dependent on interaction. This challenged the traditional notion of objective knowledge as a view from nowhere. Yet uncertainty did not lead to relativism or the abandonment of truth. Quantum mechanics remains one of the most objective and rigorously tested theories ever developed. What changed was the definition of objectivity. Objectivity came to mean reproducibility, consistency, and agreement across observers using the same experimental conditions, not access to an observer, independent set of hidden facts. The role of the observer became a central theme. Measurement was no longer passive. Observers were participants, not detached spectators. This did not mean that consciousness created reality, a popular but misleading interpretation. It meant that physical interactions required for measurement inevitably influenced the systems being measured. The observer mattered not because of awareness, but because of physical coupling. This idea unsettled long-standing intuitions about reality. People were accustomed to thinking of the world as fully formed, with properties existing whether or not anyone looked. Quantum uncertainty suggested a subtler picture, where reality is not a static inventory of attributes, but a network of potentialities that become actual through interaction. Reality appeared less like a finished object and more like an unfolding process. In philosophy of science, this led to renewed interest in questions that had seemed settled. What is a physical law? Is it a description of reality as it is, or a tool for organizing experience? Heisenberg himself leaned toward a modest realism, believing that quantum mechanics describes real structures in nature, even if those structures defy classical imagery. Laws were no longer commandments dictating behavior, but frameworks defining possibilities. Uncertainty also influenced broader cultural thought. In the early 20th century, faith in absolute certainty was already eroding due to social, political, and artistic upheavals. Quantum mechanics seemed to provide scientific confirmation that ambiguity and unpredictability were fundamental aspects of existence. Writers, artists, and thinkers drew inspiration from the idea that the universe itself resists complete control. However, Heisenberg consistently warned against overextending the principle beyond its domain. Uncertainty does not imply that anything goes, or that truth is subjective. It applies specifically to pairs of non-commuting observables in quantum systems. The macroscopic world remains stable and predictable precisely because quantum uncertainties average out at large scales. The bridge between quantum indeterminacy and everyday experience is subtle, not mystical. Still, the philosophical shock lingered. The dream of total knowledge, once fueled by classical physics, had been replaced by a more restrained vision. Science was no longer the path to absolute certainty, but to increasingly refined understanding within clearly defined limits. This humility became one of the defining virtues of modern science. The concept of reality itself was re-examined. Classical physics had encouraged a substance-based view. Objects possess properties, and interactions reveal them. Quantum uncertainty suggested a relational view. Properties arise from interactions. Reality became less about things and more about processes and relationships. This shift aligned unexpectedly with ideas from Eastern philosophy and process philosophy, though Heisenberg himself treated such parallels cautiously. In practical terms, uncertainty reshaped scientific methodology. Experimental design began to account explicitly for measurement limits. Theoretical work focused on operators, symmetries, and abstract structures rather than mechanical models. Precision was redefined, not as eliminating uncertainty, but as quantifying it accurately. Error bars and probability distributions became central rather than peripheral. Over time, what initially appeared as a loss became a gain. By accepting uncertainty, physics achieved deeper explanatory power. Phenomena such as tunneling, superconductivity, and nuclear decay became understandable. Technologies that rely on quantum behavior emerged precisely because uncertainty was embraced rather than denied. Perhaps the most profound change was psychological. Scientists learned to be comfortable with incomplete knowledge. The demand for total certainty gave way to a respect for limits. This did not weaken scientific ambition, it refined it. The goal was no longer to dominate nature with perfect prediction, but to understand its structure honestly and work within its constraints. In this way, uncertainty reshaped not only physics, but the scientific attitude itself. It taught that clarity does not require certainty, and that understanding does not demand control. Reality, as revealed by quantum mechanics, is subtle, layered, and resistant to simple description. Werner Heisenberg's legacy lies not only in an equation, but in this profound shift of perspective, a recognition that the universe is intelligible, yet never fully graspable, precise, yet fundamentally open. This transformation continues to influence how humanity understands its place in the cosmos. The world revealed by uncertainty is not less real, but more intricate than previously imagined. By accepting uncertainty as fundamental, science did not lose its footing. It found a deeper ground on which to stand. Werner Heisenberg's place in the history of quantum mechanics is inseparable from both brilliance and controversy. He was not only a founding architect of one of the most successful theories ever created, but also a figure whose scientific, philosophical, and moral choices provoked intense debate. His life illustrates how scientific revolutions are rarely clean or comfortable, and how the pursuit of knowledge can become entangled with politics, ethics, and human fallibility. As quantum mechanics took shape in the mid-1920s, Heisenberg emerged as one of its central figures. Alongside Max Born, Pascual Jordan, Erwin Schrödinger, and Paul Dirac, he helped build a framework that replaced classical mechanics at the atomic scale. Yet among these pioneers, Heisenberg stood out for his willingness to abandon intuitive pictures entirely. Where Schrödinger sought visualizable wave descriptions, Heisenberg embraced abstraction. This philosophical divide would become one of the first controversies within quantum mechanics itself. Many physicists initially found matrix mechanics nearly impossible to understand. It lacked the comforting imagery of waves or particles moving through space. Even leading scientists struggled to interpret its meaning. Some accused it of being nothing more than mathematical formalism without physical insight. Heisenberg defended his approach by arguing that physical meaning lies in predictive power and consistency, not in visual resemblance to everyday experience. This debate reflected a deeper tension between intuition and abstraction that continues in physics to this day. The arrival of the uncertainty principle intensified these disagreements. While some physicists accepted it as a natural consequence of quantum theory, others viewed it as a philosophical overreach. Albert Einstein became Heisenberg's most famous critic. Einstein admired Heisenberg's mathematical skill, but rejected the idea that nature itself is indeterminate. He believed that quantum mechanics was incomplete, and that a deeper deterministic theory would eventually replace it. The public debates between Einstein and the Copenhagen school, led by Bohr and supported by Heisenberg, became legendary. Thought experiments were exchanged like intellectual weapons. Einstein devised scenarios intended to violate the uncertainty principle, while Bohr and Heisenberg responded by exposing hidden assumptions in Einstein's reasoning. Time and again, quantum mechanics emerged unscathed, yet Einstein never conceded, famously insisting that probability could not be the final word in physics. These debates were not mere academic quarrels. They shaped the interpretation of quantum mechanics for generations. Heisenberg aligned himself firmly with the Copenhagen interpretation, which emphasized the role of measurement, complementarity, and uncertainty. Critics accused this view of being irrealist or even anti-scientific. Supporters argued that it was simply honest about what could and could not be known. The controversy highlighted a fundamental divide over the goals of science itself. Heisenberg's influence extended beyond theory into the structure of scientific institutions. At a remarkably young age, he became a leading figure in German physics. His rapid rise earned admiration, but also resentment. Some older physicists viewed him as arrogant or dismissive of tradition. Others were unsettled by how quickly quantum mechanics overturned long-established ideas. Heisenberg's confidence, though rooted in intellectual discipline, sometimes sharpened these tensions. The most serious controversy of Heisenberg's life emerged during the Second World War. When the Nazi regime came to power, German science was thrown into turmoil. Jewish scientists were expelled from universities, including many of the founders of quantum mechanics. Heisenberg, who was not Jewish, remained in Germany. This decision alone placed him under scrutiny, both during the war and long after it ended. Heisenberg's position was precarious. Nazi ideologues attacked modern physics as Jewish science, condemning relativity and quantum mechanics. Heisenberg himself was targeted by these attacks, even being labeled a white Jew by extremist factions. Despite this, he chose to stay and protect German theoretical physics from ideological destruction. Whether this was an act of courage, compromise, or self-preservation remains debated. During the war, Heisenberg became the scientific leader of Germany's nuclear research program. The possibility that he might help develop an atomic bomb for the Nazi regime has cast a long shadow over his legacy. After the war, Heisenberg claimed that he and his colleagues had deliberately avoided building a bomb, either for moral reasons or because they doubted its feasibility under wartime conditions. Critics questioned this narrative, pointing to technical miscalculations and organizational failures. The truth is complex. Evidence suggests that Heisenberg did not fully understand certain aspects of bomb design at the time, particularly critical mass calculations. Whether this was due to deliberate restraint or genuine error remains unresolved. What is clear is that Germany never came close to producing a nuclear weapon, and the reasons involve a mixture of scientific uncertainty, limited resources, and political dysfunction. The release of transcripts from the farm hall recordings, where German scientists were secretly monitored by the Allies after the war, added another layer of controversy. These recordings revealed surprise among the scientists upon learning of the Hiroshima bomb, suggesting that they had not fully grasped how close such a weapon was to realization. Interpretations of these conversations vary widely, fueling ongoing debate about Heisenberg's intentions and competence during the war. Beyond the bomb question, Heisenberg wrestled openly with the moral responsibilities of scientists. He believed that science itself is morally neutral, but that scientists are responsible for how their knowledge is used. After the war, he became an advocate for peaceful applications of nuclear energy and for international cooperation in science. He worked to rebuild German scientific institutions and re-establish trust within the global community. Philosophically, Heisenberg continued to reflect on the meaning of quantum mechanics. He wrote extensively on the relationship between science, language, and reality. He argued that scientific concepts are shaped by the conditions under which they are applied, and that confusion arises when concepts are pushed beyond their domain of validity. These reflections influenced later discussions in philosophy of science and reinforced the idea that theories are tools, not mirrors of an independent reality. Heisenberg's critics accused him of retreating into ambiguity, of using uncertainty as an excuse for lack of clarity. Supporters countered that his honesty about limits was a strength, not a weakness. The debate mirrored the broader controversy surrounding quantum mechanics itself, whether it represents a final description of nature or a provisional framework awaiting deeper explanation. Despite disagreements, Heisenberg's contributions were widely recognized. He received the Nobel Prize in Physics in 1932 for the creation of quantum mechanics. His work became foundational, taught to every physics student, and applied in countless technologies. Even those who rejected his philosophical conclusions relied on the mathematical structures he helped create. Over time, some controversies softened, while others persisted. New interpretations of quantum mechanics emerged, including hidden, variable theories and many worlds models, each attempting to address the discomfort introduced by uncertainty. Yet none displaced Heisenberg's core insight, that limits to knowledge are embedded in the structure of physical law. Heisenberg's legacy is therefore inseparable from debate. He did not offer a comforting picture of the universe, nor did he promise final answers. Instead, he forced science to confront its own boundaries. His role in quantum mechanics was not simply to provide equations, but to challenge assumptions about reality, knowledge, and certainty itself. In the end, the controversies surrounding Heisenberg reveal something essential about scientific progress. Breakthroughs do not occur in isolation from human values, fears, and conflicts. They are shaped by historical context and personal choice. Heisenberg's life reminds us that the pursuit of truth is rarely pure or simple, but it is precisely this complexity that makes scientific revolutions so powerful and enduring. Through his achievements and his controversies, Werner Heisenberg left an indelible mark on modern science. He stands as a symbol of the uneasy balance between knowledge and responsibility, between abstraction and reality, and between certainty and doubt. His story shows that the greatest advances often come not from eliminating uncertainty, but from daring to face it honestly. What ultimately emerged from Werner Heisenberg's work was not a defeat of science, but a redefinition of its power. By exposing the limits of certainty, he revealed something far more valuable, a deeper, more flexible way of understanding the universe. Uncertainty, once feared as a weakness, became one of science's greatest strengths. It allowed physics to move beyond rigid expectations and align itself more closely with how nature actually behaves. Before quantum mechanics, scientific strength was measured by predictability. The more accurately a theory could forecast the future, the more successful it was considered. This mindset worked brilliantly for planets, projectiles, and machines, but at the atomic scale it became a liability. Insisting on certainty forced physicists to cling to concepts that no longer applied. Heisenberg's contribution was to show that strength in science does not come from forcing nature into familiar frameworks, but from adapting our frameworks to nature. Uncertainty introduced honesty into scientific description. Instead of pretending that particles have precise positions and momenta that are merely hidden from us, quantum mechanics acknowledged that such precision has no meaning at that scale. This honesty made the theory more accurate, not less. By clearly defining what cannot be known simultaneously, science gained clarity about what can be known and predicted reliably. This shift transformed the practice of physics. Precision was redefined. It no longer meant eliminating uncertainty, but quantifying it. Error bars, probability distributions, and confidence intervals became central tools rather than embarrassing footnotes. Scientists learned to work with uncertainty systematically, turning it into a source of insight rather than confusion. In doing so, they achieved levels of predictive accuracy that classical physics could never reach at the microscopic level. Technological progress soon demonstrated the practical strength of uncertainty. Quantum mechanics made possible the transistor, the foundation of all modern electronics. It enabled lasers, which rely on controlled quantum transitions. Magnetic resonance imaging, atomic clocks, and semiconductor devices all depend on quantum principles rooted in uncertainty. These technologies do not function despite uncertainty, they function because of it. One of the most striking examples is quantum tunneling. Classically, a particle encountering a barrier with insufficient energy should never cross it. Quantum uncertainty allows particles to borrow energy briefly, making tunneling possible. This effect is essential to nuclear fusion in stars and to technologies such as scanning tunneling microscopes. Here, uncertainty is not an abstract limitation, but a concrete engine of physical processes. Uncertainty also strengthened theoretical creativity. Freed from the demand for deterministic trajectories, physicists explored new mathematical structures and symmetries. Quantum field theory, the standard model of particle physics, and modern cosmology all build upon the probabilistic foundations laid by Heisenberg. These theories describe the most accurate picture of nature ever achieved, even though, or precisely because they accept fundamental limits. In philosophy of science, uncertainty encouraged intellectual humility. It reminded scientists that theories are models, not mirrors of reality. This humility did not weaken confidence in science, it strengthened trust. By openly acknowledging limits, science distinguished itself from dogma. It became clear that uncertainty is not the enemy of knowledge, but a boundary that gives knowledge meaning. This attitude had cultural consequences as well. In a world often obsessed with absolute answers, quantum uncertainty offered a different lesson, that complexity and openness are not failures of understanding. They are features of reality. This perspective resonated with broader movements in philosophy, psychology, and even ethics, where rigid certainty increasingly appeared inadequate for describing human experience. Uncertainty also reframed the relationship between humanity and nature. Classical physics had encouraged a vision of domination and control. If the universe were fully predictable, it could, in principle, be mastered completely. Quantum mechanics replaced this with a vision of partnership. Nature could be understood, but not commanded without respect for its limits. This shift subtly influenced environmental thinking and the ethics of technological power. In education, uncertainty reshaped how science is taught. Students are now trained to think statistically, to interpret probability distributions, and to reason about limits. This prepares them not only for physics, but for complex systems in biology, economics, and climate science, where uncertainty is unavoidable. Heisenberg's legacy thus extends far beyond quantum mechanics into the broader scientific mindset. Importantly, uncertainty did not eliminate objectivity or rationality. Quantum mechanics remains a rigorously logical theory, grounded in mathematics and experiment. What changed was the meaning of rational explanation. Rationality no longer required complete predictability, only consistency and empirical adequacy. A theory could be rational even if it described a world where outcomes are not fixed in advance. The strength of uncertainty is also evident in ongoing research. Quantum information science, including quantum computing and cryptography, exploits uncertainty directly. Quantum encryption is secure precisely because measuring a quantum system inevitably disturbs it. Any attempt at eavesdropping reveals itself. Here, uncertainty becomes a guarantee of security, transforming a limitation into protection. Even the search for deeper theories continues under the shadow of uncertainty. Physicists still seek unification and deeper understanding, but they no longer assume that ultimate theories must restore classical determinism. Instead, they explore whether uncertainty itself might be fundamental at all levels, or whether it emerges from even deeper principles. In either case, Heisenberg's lesson remains: progress does not require certainty. Heisenberg himself recognized this broader significance. He believed that accepting limits is a sign of maturity, both in science and in human thought. Just as individuals grow by recognizing what they cannot control, science advances by acknowledging what it cannot know with precision. This acceptance does not end inquiry, it directs it more wisely. Uncertainty also protects science from ideological misuse. Absolute certainty can be weaponized, used to justify dogma and suppress dissent. A science that openly admits limits is less vulnerable to such abuse. It encourages critical thinking, openness to revision, and respect for evidence over authority. In this sense, uncertainty strengthens not only scientific knowledge, but scientific culture. As the 20th century progressed, it became clear that uncertainty had not weakened science's ability to shape the world. If anything, it had enhanced it. The most advanced technologies, the most precise measurements, and the most successful theories all emerged from a framework that embraced uncertainty at its core. The loss of classical certainty turned out to be a gain in explanatory depth. In the long view of history, Heisenberg's greatest contribution may not be any single equation, but a change in attitude. He taught science how to live with limits without surrendering ambition. He showed that acknowledging uncertainty is not a confession of failure, but a declaration of intellectual honesty. This legacy remains vital today. As humanity confronts complex challenges: climate change, artificial intelligence, biological systems, uncertainty is unavoidable. Heisenberg's lesson reminds us that progress does not come from denying uncertainty, but from understanding it, measuring it, and acting responsibly within it. In the end, uncertainty became one of science's greatest strengths, because it aligned human knowledge with the true character of the universe. The world is not a rigid machine, but a dynamic, probabilistic system rich with possibility. By accepting this, science did not lose its grip on reality. It gained a deeper, more resilient grasp. Werner Heisenberg's legacy is a reminder that the courage to admit what we cannot know is often the first step toward discovering what we can.